Welcome back, everyone. So this is a follow-up video to the Lewis relation video. And in this video, we're actually going to be using the Lewis relation to write an energy balance for wet bulb and dry bulb thermometer, using the temperature there and those different thermometers to determine the moisture in the air. So actually, what I should probably explain here is what exactly this wet bulb and dry bulb are. So we have two thermometers here, one here and one here. One is going to be wrapped in a wet cloth, and that will be our wet cloth. And one is not wrapped in a cloth; it just gives us the air temperature. So the what we actually talked about in the last video up here. Let me find it. Where is it? Right here. So the Sherwood number and the Nusselt number, we said that they actually have the same coefficients here for A, B, and C, and because of that, we can relate mass transfer and heat transfer. So what we're gonna do is we're gonna use the difference in temperatures to relate that to the difference in concentration of water or moisture content in the air. So up here we have circled in blue here these two equations for convection, convective heat transfer, convective mass transfer. So what we're going to do is, first, what we'll have here is this. So for mass transfer, we have a concentration of water vapor at the surface. And this concentration of water vapor at the surface, this is going to be our concentration of water vapor directly above the surface. So it's water vapor in the air directly above the surface. So it would be directly above our thermometer. So this is the driving force for mass transfer, and we will actually multiply that by Kc, which is our coefficient of our mass transfer coefficient. So this right here is going to be our mass transport of water from the surface to the, I guess, far away from the surface to the surroundings, whatever we want to call that. And we're going to say that this is equal to the heat transfer. So the heat transfer is going to be the temperature at the surface. And actually what we'll do here is we will do the surroundings minus the temperature at the surface, because these two are in opposite directions. So we will keep them both positive and we'll just swap these two. So this temperature difference is going to be our driving force for our heat transfer, multiplied by the heat transfer coefficient. So this is our going to be our mass flux away from the surface. This is going to be our heat flux to the surface. And one more thing we need to add in here, this is, again, a mass flux, and we need to convert this to heat. So the way we're going to do that is we're going to multiply by this lambda, which is the heat of vaporization of water. And that is going to be what relates these two together. Okay, so we're going to use the Lewis relation now. And to do that, we will divide here by Kc on both sides. So this cancels. Now this right here, if you remember from the last video, we actually wrote that the ratio of the heat and mass transfer coefficients is actually the volumetric heat capacity. So we can replace this ratio right here for just the volumetric heat capacity. And since this is the inverse, we would use the inverse of this. So I will go ahead and rewrite that. So we have a difference in concentration equals the volumetric heat capacity multiplied by the difference in temperature. Okay, so now going back to this wet bulb and dry bulb thing that we were talking about. So our temperature far away from, our temperature of the surroundings is going to come from this dry thermometer, the one that is just measuring the air temperature. This temperature at the surface is going to be our temperature of the wet bulb. So that is where these temperatures comes from. But now for these concentrations, we don't necessarily know the concentration of water vapor at the surface, which would be around this thermometer, directly above this thermometer. And this concentration of water that's far away is the concentration of water in the atmosphere that is the moisture, the humidity. That's what we're trying to solve for. So we need to find some way to actually solve for this. And the way we're going to do that is we're going to replace these concentrations with partial pressures. So we will come down here. There we go. And we still have our heat of vaporization of water. But now we have our partial pressure of water at the surface, which again is the partial pressure of water vapor directly above the surface. It's a little bit misleading when we say at the surface. It's not exactly on the surface, it's directly above the surface in the air. And we divide by our gas constant and temperature at the surface. And then we're going to do the same thing for our concentration far away. Okay. Now, we know that from the ideal gas law that the density is equal to the total pressure. Let me make sure I'm thinking about this right. Yeah, it would be the total pressure divided by our gas constant again, and then we would take the average pressure, or the average temperature. So we will put that in place of density. And then we have our difference in temperatures again. And we don't need to do anything with these because these actually just come from our thermometers. Now, we want to simplify this a little bit. And the way we're going to do that is going to be with these temperatures here. Temperature at the surface, temperature far away from the surface, and the average temperature. And we're going to make a sort of, well, let me put it like this. If these temperatures are in Kelvin, so these temperatures might be something like 300 Kelvin, 305 Kelvin, and 310, something like that, where these temperatures are very close together. Now, if we were to measure these in Celsius, they would still be 5 apart, but that would be a much higher percentage away from each other. I hope that makes sense. But when we add 273 to all of them, now they're relatively a lot closer together. And because of that, we're going to just say that they're close enough to each other to be the same. And because of that, we can cancel this, this, and this. So they're not exactly the same, but this is just a simplification that we're going to be using to make the problem simpler. Now, we're not going to do that for this temperature here and this temperature here, because if we were to do that, it would be equal to 0, and then there would be no point to this. So we're still going to keep these as they are. So now that these are canceled, what we're left with is our pressure at the surface, our partial pressure of water at the surface, minus our partial pressure of water far away from the surface, equals the total pressure multiplied by the temperature difference. And finally, now we come back to here where this partial pressure of water far away from the surface or in the atmosphere is what we're trying to solve for. We're trying to solve for that. But this partial pressure of water at the surface, we actually can get this. So this is going to be the saturation pressure of water at the surface. And we're actually able to calculate that by using, we can look it up in a table, or we would actually calculate it using something like the Antoine equation. So finally, we have this saturation pressure of water at the surface minus the partial pressure of water far away from the surface. Again, this is what we're trying to solve for. Total pressure times the temperature difference. And this, get red for this, this is our energy balance. So we are going to use this in order to actually find what the humidity of the air is using the two thermometers. So that is going to be all for this video, and I will see you all in the next video. Thanks for watching.